Skeletal muscle cells and neurons are excitable. This doesn't mean that they're prone to outbursts whenever they get happy. It means that they can respond to stimuli. You can think of it as having an on switch and an off switch, like the light switch of a classroom, where you flip it on and there wouldn't be an on position to flip on if there was no off position. It reminds me a lot of the movie Inside Out, which dates me because it came out a while ago. It's a kids' movie, Pixar movie, about emotions. One of the morals of the movie is that there can be no happiness without sadness, that both emotions have a role to play. To relate it to muscle cells, for the muscle cell to be excited, to be stimulated, it has to have a resting stage too. That stage is called resting membrane potential. It describes the conditions that the cell is in whenever it is at rest, not being stimulated, not contracting. Because of the name, you might think that the cell isn't doing anything to maintain this stage. But many cells, like muscle cells and neurons, expend a whole lot of energy in order to maintain this resting stage, up to 70% of their ATP. When the cell is at rest, it is exhibiting resting membrane potential. The resting, of course, means that the cell is resting and not being stimulated. Potential refers to potential energy. While nothing is happening, the potential for something to happen exists. The cell at resting membrane potential is said to be polarized. Polarized refers to the fact that there are two poles or ends, a charge difference and concentration difference between the inside and outside of the cell. This is called an electrochemical gradient. The electro refers to the charge difference, a difference in voltage, negative versus positive. The chemical refers to a difference in the concentration of ions. Here, those ions are sodium and potassium. Na plus equals sodium, K plus equals potassium. How is the cell polarized? What is the difference? Voltage difference, again negative versus positive. The outside of the cell is comparatively more positive than the inside of the cell. This is due to the concentration difference. The outside of the cell has a relatively high concentration of sodium ions, while the inside of the cell has a relatively low concentration of sodium. Potassium is going to be more plentiful inside of the cell. This is due to three factors, really. The first factor is there are more potassium leak channels than sodium leak channels. Thinking back to chapter 3, remember a leak channel is a protein channel in the membrane that is always open. There is no gate, there is no lock. It is open all the time, continuously allowing ions to pass through it into or out of the cell. The second factor is that there are lots of large negatively charged molecules like proteins and ATP that are so big they are stuck inside of the cell. Just like that one friend in your friend group who's always complaining and never seems to be happy, these molecules are going to impart their negative charge all throughout the cell. Makes the whole cell negative, just like your friend kind of brings the whole vibe of the group down. So inside of the cell is negative. Right? This is just part of the cell. And we've got these large proteins inside here. They have a negative charge, making the whole interior of the cell, including this area right underneath the cell membrane, negative, versus positive charge on the outside. Now, you'll see that both of our ions have a positive charge. Right? So sodium Na plus, potassium K plus. So positive charge for both. This means that both ions are attracted to the negative interior of the cell. Positive is attracted to negative and vice versa. Positive wants to diffuse to negative until there is no difference in charge. So both the sodium ions and the potassium ions located outside of the cell want to cross the cell membrane and head towards the inside. We'll just make that positive. Potassium is positive. Now, there's plenty of potassium leak channels. So potassium has no problem using those leak channels to diffuse into the cell. Woohoo! Potassium says. It's potassium night at the club. No restrictions. Positive potassium ions head towards that negative interior and get down inside of the cell. Sodium wants to come inside too. Sodium is positive too, right? It wants to go, it wants to come in and have a good time. However, most sodium channels are gated channels. And again, thinking back to chapter 3, remember that gated channels do have a gate that locks. So they're usually closed. And it takes a special key to unlock that gate and allow passage to occur. That key might be a specific voltage or electrical charge. It might be a substance like a neurotransmitter or hormone. There are a few sodium leak channels, so a little bit of sodium can come inside the cell, a little bit. But most sodium, I won't do the pluses here just for time purposes. Most sodium ions are trapped on the outside, wanting to get in, right? They want to get in towards that negative charge. They just aren't able to do it. They are trapped on the outside, unable to get into the cell. So we have these two very important reasons why resting membrane potential exists, right? Number one, the cell is more permeable to potassium because there's more potassium leak channels to allow that potassium to come in. So we get more potassium in here. Number two, there's a lot of these large negatively charged molecules in the cell that make the whole cell negative. So there's a difference in concentration and charge. However, if the cell was just left like this with nothing else going on, these differences, this electrochemical gradient, would eventually cease to exist. That is because of diffusion. It would take some time, but eventually we're going to get enough sodium going through the few leak channels that are present to disrupt this concentration gradient and allow enough sodium ions in so there's no concentration difference. Equal amount of sodium inside and outside. With potassium, this movement in would eventually cease whenever the concentration became equal. Diffusion just keeps on going until there is no difference in concentration and everything is even, everything's balanced out. We didn't talk about this in chapter 3, but the same thing happens for voltage. Eventually, we get enough positive ions inside of the cell to counteract the negatively charged proteins. And it would be the same charge inside versus outside. So these two factors are important, but without something to help out, they are unable to maintain the resting membrane potential all on their own, and the cell would lose that polarization, lose that off switch, be unable to be stimulated. So what is it? What is going to help the cell maintain resting membrane potential? It is the sodium-potassium pump. This is a protein that we talked about in chapter 3 because it was a great example of active transport. Transport that requires energy, must be fueled by ATP. That's because active transport goes against the concentration gradient and transports substances from low to high concentration. Quick recap, Recall, diffusion is always movement down the slide, down the hill, from high to low concentration. And it doesn't take energy to roll downhill, right? So this passive transport does not require ATP. However, active transport moves substances uphill, up the slide, from high, from low to high. And it does take energy to push something uphill. So active transport does require ATP energy to fuel it. As we learned previously, the sodium-potassium pump uses ATP to pump out sodium from where there's less of it to where there's already a lot outside of the cell, and transports potassium from where there's less of it outside of the cell to where there's already a lot inside. So you can see here, it's going to pump out 3 sodium ions for every 2 potassium ions that it pumps in. So this is going to maintain that high concentration of sodium outside, high concentration of potassium inside, in the face of diffusion. Again, active transport. So even though this is called resting membrane potential, the cell is not at rest. The cell is working hard to maintain these conditions. This diagram from your book shows these conditions that the cell maintains during resting membrane potential. We see that there are large negatively charged proteins inside of the cell, making the inside negative. There is an uneven distribution of ions as potassium follows that charge into the cell. So lots of these potassium leak channels, potassium comes into the cell, attracted to that negative charge. Sodium is positively charged as well, so it wants to come in, but there are very few sodium leak channels. And then here we see that amazing sodium-potassium pump that kicks out the few sodium ions that do diffuse in, while kicking in any of the potassium ions that happen to diffuse out. So in this way, resting membrane potential is maintained. Negative charge inside, lots of potassium inside. Positive charge outside, lots of sodium outside. And this shows that resting membrane potential condition as well. The charge difference and the chemical difference of the electrochemical gradient. This is going to occur in the skeletal muscle cell, when the muscle is at rest, and, little preview, occurs in the neuron when the neuron is at rest. And through this resting membrane potential, we have an off position, which means we can also have an on position. So, we've spent a lot of time talking about the cell not contracting, not being excited. Now we can talk about what excites the cell. This is called an action potential. Action potential is our signal, or our stimulus. It consists of two big phases called depolarization and repolarization. So that uses that term polar we just talked about, right? When the cell is at rest, it's polarized with two poles, like North Pole, South Pole, two ends, negative, positive, potassium, sodium. Depolarized, then, is flipping that condition over. So the cell is going to increase its positive charge, become more and more positive as more and more positive ions come in. When the cell reaches a certain voltage, becomes a little bit more positive than resting, this will then kick open all the gated sodium channels. So this is the key that unlocks these gates. It's the specific voltage. When the sodium channels are open, sodium is allowed to diffuse, right? Go past the membrane. We just talked about how there was lots of sodium trapped outside, not much inside. Diffusion takes us from high to low. So sodium has been waiting for this. It's been ready and waiting in the extracellular environment. It's going to rush through those now open gated channels into the cell, from where there's a lot of it outside to where there's less of it inside. When it does this, it rapidly makes the cell more and more and more positive until it goes past 0, positive 10, positive 20, about positive 30 millivolts. So the cell is now firmly positive. The cell is being signaled or stimulated. This is followed by repolarization, or a return back down to resting membrane potential. That specific positive charge is another key that now locks those gated sodium channels. So they slam shut. Sodium cannot pass through the membrane anymore. That same key causes the gated potassium channels in the membrane to swing open. Remember, there's a lot of leak channels that are potassium, but there's also gated potassium channels. So when these swing open, they contribute to the passage of potassium, allowing potassium to move through the membrane. Potassium was the opposite of sodium, in that there's a lot of potassium inside of the cell and not much outside. So when all these additional gated potassium channels open up, that means that potassium now is going to diffuse out of the cell even more. So all those positive potassium ions leaving carries with it that positive charge. We go back down, 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 down to negative resting membrane potential. A lot of times you'll see a graph along with these diagrams of these two situations where we have around -70 is resting membrane potential. And then a stimulus will allow some sodium channels to open up. The cell gets a little bit less negative. And around -55, that's our key that swings those gated sodium channels open. So, whoa, lots of sodium coming in. Picks us up past 0 to about positive 30 millivolts. So past 0, past 10, 20, we get to positive 30 millivolts. Kind of ran out of room. MV for millivolts. And then that causes those sodium channels to slam back shut. Potassium-gated channels open up. As potassium leaves the cell, we go back down, down, down. So 30 down to 20, down to 10, past 0, all the way down, 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 down. We stabilize back at -70. We're back down at resting membrane potential. So putting that together, we've got our action potential, which is a rapid depolarization, then repolarization of the cell. This works to signal the cell and excite it. Resting membrane potential, -70, cell is at rest. Again, lots of potassium inside, lots of sodium outside. Then cell is stimulated, undergoes depolarization. These sodium channels, gated sodium channels open up. Positive sodium ions rush in, carrying with them this positive charge, making the inside of the cell positive. So the cell is excited. Maybe you think when we're positive, we're happy, right? Happy, excited. So positive, excited, woohoo, being signaled. And then, once we get to that positive range, that triggers sodium channels to close up, slam shut. Sodium doesn't come in anymore. Potassium, that's a leak channel. The potassium gated channels open up. And positive potassium ions leave the cell. Again, taking with them their positive charge. So the cell returns back, down, 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 down to negative resting membrane potential. And again, this is called an action potential. A rapid change in charge across the cell membrane. Negative, up to positive, back down to negative. When the cell is stimulated, as rapid depolarization occurs, followed by a rapid repolarization. As I said before, both neurons and muscle cells are excitable, so they both experience action potentials when they're stimulated. Muscle responds to an action potential by contracting, by shortening. So the sarcomeres are going to move whenever the cell is stimulated in this way.